Hi, this is Calculus 12, Chapter 4.2. We want to recall the intermediate value theorem, that if a function f is continuous, then there exists a c in between a and b such that f of a is less than f of c is less than f of b. And it's an existence theorem, so it doesn't say what the exact value is. It just says there's going to be a value. So that leads us to the mean value theorem. If y equals f of x is continuous on a to b closed and differentiable on a to b open, then there exists a c in the open interval a to b such that the derivative at c equals f of b minus f of a over b minus a. And recall, this is the average rate of change of f on that interval. And another way to write that is delta f over delta x. So the change in f over the change in x, and that's rise over run. This is also an existence theorem. Recall that mean is an arithmetic average, but we are looking for the average rate of change. For an arithmetic average, we add the values and divide by the number of values. So this looks different. This is more restrictive than the intermediate value theorem because it needs to be differentiable, but we can usually solve for c. Here's a graphical look at what we're dealing with. So the mean value theorem is not applicable here. It has to be differentiable on a to b, and the derivative does not exist here. Okay, again, this is not applicable because the function is not continuous on the closed interval a to b. Not continuous. Here, the mean value theorem applies. Average rate of change is this, and we can find a parallel line. Okay, this is continuous and differentiable, and the average rate of change is that. We can see that the slope matches here, and the slope matches here. And similarly, the mean value theorem tells us that there's at least one slope that matches. There can be more than one, but it doesn't say anything about that. Let's look at some more definitions: increasing functions and decreasing functions. Let f be a function on an interval I, and x1 and x2 are on the interval I. x1 cannot equal x2. Then f is an increasing function on I if x1 is less than x2, and the value f of x1 is less than the value f of x2. F is a decreasing function on I if x1 is less than x2, and we have f of x1 is greater than f of x2. And we don't prove these definitions, we just understand them and use them. So corollary 1 on increasing and decreasing functions. Let f be a continuous function on a closed interval a to b and differentiable on the open interval a to b. If the derivative is greater than 0, i.e. positive, at each point on the open interval a to b, then f is increasing on the closed interval a to b. If the derivative is negative at each point on the open interval a to b, then f is decreasing on the closed interval a to b. And the reason why we have theorems is we use them to prove bigger concepts. And we're using the MVT to prove that the functions are increasing or decreasing. So we have to start off with our definitions. Let x1 and x2 be on the closed interval a to b. x1 does not equal x2. Now we use the mean value theorem. F prime of c equals f of x2 minus f of x1 over x2 minus x1 for some c in the open interval x1 to x2. This leads to f of x2 minus f of x1 equals f prime of c times x2 minus x1. We're just rearranging our equation here. And what we want to note now is we know this is positive. x2 is greater than x1. That's from our definition. Now, what we need to note is we have two factors here. This is one factor. This is another factor. And because this is positive, the signs must match. Okay, so if this is positive, then this must be positive. If this is negative, this must be negative, because a positive times a positive is positive. A negative times a positive is negative. And now we can write our conclusion. So, if f of x1 is less than f of x2, then and the derivative must be positive, and f is increasing. Similarly, if f of x1 is greater than f of x2, then the derivative is negative and f is decreasing. And QED. Quod erit demonstratum. Let's think about the intermediate value theorem. What has to happen for an increasing function to become a decreasing function and vice versa? Well, it has to go from positive to negative. That means it has to go through 0. So we're looking for zeros. Okay, corollary 2, functions with the derivative equal to 0 are constant. If the derivative is 0 on the interval I, then there exists a c such that f of x equals c for all x on the interval. Corollary 3, functions with the same derivative differ by a constant. If the derivative of f is equal to the derivative of g at each point of an interval I, then there exists a c such that f of x equals g of x plus c for all x on the interval. Okay, so if we have f of x equals a sine x, the derivative is cos x. If we have g of x equal to sine x plus 10, the derivative is cos x. Okay, so the derivatives are the same. We go backwards, actually. F of x could be sine x, and g of x could be sine x plus 10. It could be sine x plus 20. This could be sine x plus 30. They differ by a constant. Our next definition is antiderivative. A function capital F of x is an antiderivative of a function lowercase f of x if capital F prime of x equals lowercase f of x for all x in the domain of f. The process of finding an antiderivative is called anti-differentiation. Okay, we're just going backwards. So let's look at a couple examples. From example 28, f prime of x equals sine x. Therefore, f of x equals negative cos x plus c. By convention, we don't need brackets here because parameters are always a single term. So if we left the brackets out, it means cos x, and then we add c to the whole value. It's not cos of x plus c. Okay, next one. And I'll give you a clue here. F prime of x, if we're given f prime of x equals x to the power of n, then the antiderivative is x to the power of n plus 1 over n plus 1 plus c. Note, the plus c is not part of the numerator. It's added to the rational. Okay, so we have f of x equals, let me put that in a box. We have x to the power of 4, 8 over 4, because n is 3, and then plus c. And we want to simplify this. 8 divided by 4 is 2. So just use this formula, or you can just work backwards on the power rule. Let's look at some more examples. On page 192, exercise 18, f of x equals ln x minus 1 from the closed interval 2 to 4. And we want to use the mean value theorem to find our c. Okay, so the average of f, the average rate of change, equals delta f over delta x. That means we have f of 4 minus f of 2 over 4 minus 2. That's ln 3 minus ln 1 over 2. Ln 1 is just 0, so we have ln 3 over 2. Leave this as an exact value. The derivative of f is 1 over x minus 1. The derivative of this is 1, so we multiply by 1. But that's just 1 over x minus 1. Now we want to solve for our c. So we have 1 over c minus 1 equals ln 3 over 2. We cross multiply. We get 2 equals c minus 1 ln 3. So we get c minus 1 equals 2 over ln 3. And c equals 2 over ln 3 plus 1. I'll just make that too clear. And that's your final answer. Please don't give me a decimal value. Leave it as an exact value. Okay, question number 24. Again, we want to find the c that matches the average value. This is a piecewise function. It's not differentiable at x equals 0. So strictly, we can't use the MVT because it's not differentiable at x equals 0. But we can try on A since it's continuous and differentiable, and on B because it's continuous and differentiable. Graphically, it looks like this. And we're going to have an answer here. We're going to have an answer here. And we also actually have an answer down here. So there should be 3 solutions. Always check graphically to know how many solutions you need. But we'll do it analytically and make sure that it matches. Okay, so we start. We'll just do some intermediate calculations here to make it a little bit easier. So f of negative pi, we use the first piece of the function, cos negative pi, and that equals negative 1. F of pi equals 1 plus sine pi, and that equals 1. So delta f over delta x equals f of pi minus f of negative pi over pi minus negative pi equals 1 minus negative 1 over pi minus negative pi. And we get 2 over 2 pi, but that's just 1 over pi. Okay, so we'll call this function A, call this function B. So we have A prime of C equals negative sine C equals 1 over pi. That means C prime, we want the reference angle equals inverse sine of the absolute value of negative 1 over pi. That is approximately, this one's okay to use decimal values, 0.3239. Now, we have to draw our chart here. All students take calculus. And this is negative. So we have an answer in quadrant 3 and quadrant 4. This is 0, and we're going in this direction, and this is negative pi. So we have 2 answers here. So our quadrant 3 answer is pi plus 0.3239, and that gives us approximately 3.4654. But we have to subtract 2 pi in order to get the coterminal angle. So 3.4654 minus 2 pi, and that gives us approximately negative 2.8177. Our second answer is in quadrant 4. That's 2 pi minus 0.3239. That's approximately 5.9593. And now we need to subtract 2 pi to get our coterminal angle. And that's approximately negative 0.3239. So that's 2 answers. B prime equals cos C equals 1 over pi, our average rate of change. So C prime equals inverse cos 1 over pi, and that's 1.2469. Again, we have our chart. All students take calculus. We have cosine positive in those 2 quadrants. We're going from 0 to pi in this direction. So we don't need a quadrant 2 answer. We just need our quadrant 1 answer. This is already a quadrant 1 answer because it's our reference angle. And we're done. And that completes this lesson.